Hi everyone, this is Han from the Northeastern University in Boston. Today I'm going to present our research regarding the behavior modeling and its corresponding digital pre-distortion techniques for the nonlinear power amplifier in the modern wireless system. This work has been done by me and my colleagues from the Northeastern University and the Maynooth University in Ireland. It's under the supervision of Professor Miriam Leeser and Professor Dooley. In this work, we propose this new computationally efficient lookup table-based digital pre-distortion for wireless systems that have multiple standard signals. In the modern wireless systems, this nonlinearity of the power amplifier will actually cause a spectral regrowth like shown in this figure right here. It will introduce the interference to the adjacent channel and before the Dpd system, people usually use the back-off strategy to make sure that the PA is operating at a linear region. This will actually cause the power inefficiency, especially under the current OFDM-based modern wireless system, where the signal's peak to average power ratio is relatively high. I think there are three key aspects of the Dpd system. And the first one is the linearity, of course, and the second one is its power efficiency, and the third one is the flexibility. So the modern Dpd system should be able to maintain the linearity property while increase the power efficiency. And besides that, we also hope that the Dpd system will provide us some flexibility that will cooperate with different signals. For this work, there are mainly three contributions for the community. First, during our research on other Dpd works, it seems that most of the work are focusing on a single standard signal, and also their PA are working under the same input power levels, so their models has limited flexibility. Hence, we propose these common behavior models for signal of different standards like 3G signal as WCDMA signal and 4G signal as LTE signal and 5G NR signals, and with different power levels. After proposing the model, we actually implement a real-time Dpd system on the FPGA, the RF-SOC from Xilinx, which increase the power efficiency of our system. The state-of-art Xilinx RF-SOC has 16-bit stacks with 10 gigasamples per second sampling rate. Our parallel processing Dpd system will allow us to match the speed of this next-generation RF front-end. Because of this work is a collaboration work between us and Maynooth University, we have actually set up two individual test benches with different PAs from the different manufacturers and ran experiments on them. This will further prove our theory and our models. One of the traditional ways of building the Dpd system is to use the behavior modeling method to describe the PAs and then apply the reverse model to the input signals. Among these models, the Volterra series-based model are mostly studied and used. The Volterra series is generally used to describe the nonlinear system as it has the ability in capturing the nonlinearity and the memory effects of the system. However, the most used model in Dpd design are actually variants of the Volterra series, for example, the memory polynomial model or the generalized memory polynomial model. They have reduced complexity but with similar performance compared to the Volterra series. The equation on the left shows the MP model. It's basically the sum of the input samples in past times with different orders and multiplied by a pre-trained coefficient APM, and also where this P stands for the order of the model and the M stands for the memory types of the model. The equation on the right is a little bit complicated than the MP model, but it's more accurate as it has more terms like the cross multiplication terms at different timestamps with different orders. Similarly, they have coefficients like AKL and BKLM and CKLM, and the least square methods are generally used to obtain these model coefficients. However, these least square methods are not really hardware friendly. It is really hard to extract them using the hardware like FPGA or ASICs. And also, most of the research are only targeting one signal standard, so it requires retraining for the model when changing to a different signal standards. Another approach for the digital pre-distortion, but in a relatively easier way of doing it, is to use the lookup table-based system. For each sample of the input signal, the system will pre-distort the signal solely based on the gain and the phase of the current signal samples. This actual mapping relationship between the input and its response are stored in the lookup tables. While although it's hardware friendly and people can easily implement them on the FPGAs or ASICs, that does not actually account for the memory effect. And similarly to the previous approach, it's only handle one signal standards, and it requires redescribe the model when changing to different signal standards. So our work come up with this common Dpd system that will deal with the disadvantages of the previous system, and this design is based on an observation of that the PA is actually behaving similarly when the input signals with different standards are set to be at a proper power levels. It is more clear when we look at the figures here. So these figures are the Amm curves of the signals that are under different signal standards and different power levels. The Amm curves, which is the amplitude to amplitude modulation curves, is generally used to describe the input-output relationships of the PAs. The figure on the left, we have 3 different signals, which are shown as 3 different curves: the blue, the orange, and the red one. These curves are generated when these signals are at different standards, but at the same power levels. So as you can see here, these curves are not overlapping, so that means the PAs are behaving differently with these signals. However, after tuning the signal power levels, we got the figure on the right. The curves are actually overlapping, which indicating that the PA is behaving similarly. So, in a word, if we selected the power level properly, the signals of different standards could actually be described by one common model. With the previous property in mind, we can actually build a Dpd system where we use multiple sets of coefficients to describe the PA's behavior under different input signal powers, instead of solely using one set of coefficients. Here is an illustration of the design. We will start with input signals that have different standards and different power levels, like a 3G signal in power level 1, a 3G signal in power level 2, and a 4G signal in power level 1, and so on and so forth. Initially, we first deal with the power levels. We train the different coefficients for each power level signals so that we can have a mapping like this. We have a set of coefficients for each power levels and each signal standard. However, if we utilize our property in the last slide, we can actually combine the lookup tables and reduce the total number of them, because as we shown before, the input signals from different standards could have similar PA models with proper power levels. For example, in the illustration here, the 4G signal in power level 1 could share the same set of coefficients as 3G signal in power level 2, so that we can reduce the total number of the coefficient sites. Therefore, our model will deal with signals in multiple standards, but still constrain the design in a smaller set. We only need to use one standard signals for training and store them into the hardware. Here is the further experiment setup for the data collection. We have collected more data among multiple power levels and built a mapping relationship between different standards. This setup will give us the fundamental observations and verifications for our proposed common PA model. In this setup, a Xilinx RF SOC CC111 is used as our RF frontend. It is solely served as a dump pipe. There is no Dpd data processing on the board, and we then connect the signal to Dooley PAs from the RF HIC, and like this, which is a black box on the left, and then we collect the data using the spectral analyzer and do the analysis afterwards. This table shows the results of the previous data collection. The table 1 here provides the actual mapping relationship between signals with different standards and the power levels. For example, in first column here, as you can see, the 5G signal with minus 10 dBFS and the 4G signals with minus 18 dBFS and the 3G signals with minus 20 dBFS are sharing the similar coefficient sites. We try to maintain the model performance in a acceptable range, and this we will discuss in the next slides. And then so on and so forth for the other power levels. These results have proved that we can actually build a PA behavior model using a common set of coefficients to deal with signals with multiple standards, or in other words, we will train the model with signals with one standard but apply them to signals with multiple standards. The table 2 here shows the accuracy of our common behavior model, where the results are shown in NMSE in dB, where the NMSE stands for the normalized mean square error. It is generally used to measure the performance of PA's behavior model or DPD performance. The cells that are colored are the test signal performance and the PA if we train them by the signal of their original standard. So the other cells are NMSE results for sending the same test signal, but the coefficient sets are extracted using another signal with different standard. The column here actually shows that if we train the model with solely the 3G signals and how these test signals are going to perform. As you can see, there is some manner or a few dB performance drop comparing to the trainings with the original standard. The graph here the table here verified our PA's models, and based on that, we can build a Dpd system that inverts the model for the pre-distortion. So our proposed system is actually a lot-based Dpd system for multi-standard cognitive radio. Only one signal standard, but at different power levels, are used to extract the sets of coefficients as a common Dpd model. And then we store these pre-trained sets of coefficients as lots. And with proper mapping the signals with different standards, we can have this common model. And after all of this, we can implement it on the FPGA for the real-time processing and power efficiency. And this is the hardware overview of our design. The DPD core is actually running on the FPGA like shown here. Instead of our previous test bench, the FPGA solely served the purpose as a PAP. The test signal on the left is generated from a hosted PC and sent to the board through the Ethernet. The signal stimulus block will send them to the address selection module where the lot is selected and then updated to our DPD model. The memory polynomial core here is actually the DPD model, and the signal is sent to the DPD core for the processing. Afterwards, it is sent to the RF digital front end, which is connected to the RF DAC. So this picture here shows our actual setup for the DPD system. Another PA and SDR is in use. The tested PA is from the NXP and is also a Dooley PA. And the RF front end is the Xilinx RF SOC Generation 3 ZCU216. Also, we have this variable gain driver PA that will control the input signal power level so that the PA is saturated in different status. This graph here shows the result of our hardware implemented DPD system. It shows that 3 different models where their coefficients are extracted use the signals with different standards, and their performance under same set of test signal at fixed power level. Similarly to our previous simulation results, this hardware design results also show some minor loss comparing to training with its own signal standards. And in conclusion, that in this work, we actually explore the PA's behavior for signals with different power levels and standards. And after that, we we implemented a hardware DPD system with linearity, flexibility, and efficiency. And in the end, our experiments are running on 2 separate and individual Docker DPAs from different manufacturers, which then further prove our series and our DPD systems. And that will conclude my presentation, and I would like to thank you to MathWorks and Xilinx for their generous donations.